In this subVI, we need to first form a sinusoidal carrier wave, and then we can multiply that by the incoming signal. That becomes our product modulator. I'll begin by forming the front panel controls for this subVI. We need our first array to establish the connection point for the incoming signal. We also need information about the bit interval t sub b, that has units of seconds. And we'll need a few more. This would be the carrier frequency in hertz. And then we also need the sampling frequency in hertz. Now the main built-in subVI of interest is the sine wave generator. And let's review the inputs to this device. Get the context help going. And we have the total number of samples to generate, the amplitude, the frequency, and if you wanted to, you can adjust the initial phase. We'll just leave the default for that. And then we generate the sine wave as an array of sample points on the output. Now, different subVIs use different definitions for frequency, and it's important to check the help page for each one. This one in particular uses normalized units in cycles per sample. So many other subVIs will just work with hertz directly. This one is an exception to that. So we can take the carrier frequency and divide that by the sampling frequency, and that gives us a normalized frequency between 0 and 1, which is what this subVI expects. Now, in order to give the sinusoidal carrier the effect of having unit energy per bit, we need to do a little bit of scaling, and we need to form the scale factor 2 divided by the bit interval, and then the square root of that quotient. And that produces the required amplitude for the sinusoidal carrier. Next, we need to determine exactly how many samples to produce for the sinusoid, and we do this based on the size of the incoming signal. Find the size of the signal in array and then use that to generate the number of samples. Lastly, the point of the modulation process then is the product of the incoming signal and the sinusoid that we've generated. Let's go ahead and create an indicator, and we're all set. And now I'll make a few comments about the waveform data type. The subVI specifications ask you to use the waveform data type for both input and output. So begin with the get waveform components node. It's easy to make a front panel control for that. If you pull this down to expose other attributes, pick the one called DT, abbreviation for delta time. Anytime that you need the sampling frequency inside your own subVI, go ahead and just do a reciprocal operation on that, and now you've got the sampling frequency associated with that waveform in units of hertz. The nice thing about waveform data type here is that you're bundling together the array of your signal with the timing information, in this case the sampling frequency. Now, just by way of illustration here, I'll use the quick scale as my operation that's going on inside this subVI that operates on the double 1D array. As you've generated something that needs to be sent as an output, use the build waveform array node. And I'll show you a couple different ways of doing this. One is to do similar to what you did before, expose the attribute for delta time, and simply connect that back to your original delta time that you knew about. So now you're able to create a waveform by bundling those two pieces of information together. An alternative method that sometimes works nicely is if you already have a waveform that's very close to what you need. In this case, of course, it has the correct delta time associated with it. Then you can simply wire that to the top of your build waveform, and then when you wire in the value for y, it simply replaces the signal with your new signal. Creating an indicator is likewise easy.